Okay, my name is Jungsoo from Samsung Memory, and I have a co-presenter, Dr. Kwon from the Mangoboost. I'm taking charge of developing full-fledged storage system, and today I'd like to go over briefly and walk through what the Petabyte-Scale storage system is, and what the challenges are. And one of the areas that we are looking at is the more efficient and more reliable storage, ultra high density system. And we worked with the Mangoboost to test the more efficient new platform based on the DPU. So Dr. Kwon will introduce the more details of our findings from our POC result. So Petabyte-Scale storage system we call PBSS. So I think there's no doubt that in the AI era, the high density and disaggregated storage system is a trend, and there's a lot of news on such a system. So we named the Petabyte-Scale because the one single system can easily accommodate more than Peta-Scale with multiple SSD devices. So we targeted on the storage source system in the data center cluster, and the PBSS will act as like a SSD in our data system scale, and data center itself will be acted like a computer. So we have developed, this is the first version of PBSS, and we have offered 4 different types of configuration based on the applications needs. So type 1 system utilized accommodates 32 U1.S1T SSDs, and with 32 terabytes of devices, the box can offer 1 petabyte of capacity in the box. Type 2 system is for SSDM, and in the middle there are 8 U.2 drives. That is for the SSDM drives, and so some of the file system requires to have faster and better latency to store the metadata and buffer space. And type 3 is for the high performance application like a database, and each drive offers by 4 PCI lanes, and it offers the best performance among the 4 different types of system. And type 4 is for the new devices like CXL devices, and the system accommodates 4 different types of E3.2T devices, so that the CXL device can be installed on the system. So what are the challenges and solutions on such an ultra high density system? We are looking at 5. We have found the 5 different categories on the challenges: the power and TCO and reliability and performance and data protection. In terms of the power, with the EDSF E3 drives, Gen 5 drives, the typical power consumption is over 21 watts. So if you think about, you have 21 watt drives in a single system, 32 20 watt drives in a single system, the power itself can take up more than 50% of total system power. So power is the critical point on such ultra high and high performance system, and we are studying the technology that we can reduce and capping the power. And the TCO is also the concerns on such a ultra dense system. Not only the NAND, but the controller. We need a high performance and expensive CPU to process the workload of the system. So we're looking at the new platform to lower the TCO in terms of the OPEX and OPEX, CAPEX and OPEX in the data center. And reliability and performance and data protection, like I read and you see, if you have 32 terabyte device, you will need some kind of protection mechanism because the rebuild effort and resource takes us so much. So those are the areas we are looking at, and there's some solutions we are studying right now. So power management solution to manage each SSD power of the storage system, and flash storage module to enable the efficient storage devices in the system, and the new storage platform. And we are looking at the better and better way to protect the data in the device level and the system level. So, and for in terms of platform, the DPU is the one of the area, and that's why we have worked with the Mangoboost to test the efficient way to process in the Petabyte-Scale system. So I'd like to hand over the mic to Dr. Kwon to explain the more details about our findings on DPU. Thank you.
Thank you for the nice introduction, and thank you for being here. My name is Dongup Kwon, and I work at Mangoboost. Before getting into the tech parts, let me give a brief introduction on our company and our history. So we are a DPU solution provider, and our mission is to solve any inefficiency problem in data centers and to make the data center sustainable for the future. And we believe that the DPU and the new computing paradigm driven by the DPU will be the best approach for to get to that point. And the key idea of DPU is offloading and accelerating the infrastructure management task to the new component in a server in a very transparent way. And this is our history. We are system people, and our background are computer architectures and computer system engineering. We have been doing this work for more than 10 years, and some of you might not be familiar with the conference names, but we have many experience on designing very specialized DPU architectures, and we have made a lot of prototypes and published our outcomes to the global top-tier computer architecture and computer system conferences like ISCA Micro and OSDI. And we decided to commercialize our technologies to go beyond the research lab in the university. Our solutions and our business models are very unique. Our first product is a composable DPU architecture on a off-the-shelf FPGA devices. And you may have questions like that. What is the composability in DPU world? I know about Bluefield, Pensando, and Oak Spring Canyon, but I never heard about the composability in DPU world. And here is the answer. So we have a bunch of hardware acceleration IPs, and in many different domains. And then we try to understand the need from customers and our partners, and we try to understand their target specification and their killer applications. And then we figure out what is the performance bottleneck and what is the critical path in their infrastructure right now. And we designed the customer-driven DPU architectures for very specific to that customer's infrastructure and environments. So by composing some of our hardware IPs into a single FPGA product, that's the composable DPU solution we can provide. Then the output could be AI optimized DPU, or it could be storage optimized DPU, or it could be network optimized DPU solutions. But they have all different subset of the hardware acceleration IPs. That's the point. And then we implemented the architectures on FPGAs with full software support. This is how we collaborate with Samsung as well for this project. Then let's jump into the petabyte storage solution and system. And when I started this project with Samsung, I was very surprised that because a single server and single box can have 16 high-end SSD in it. And another point that surprised me is that basically it is supposed to around 40 million IOPS performance. So ideally, so we started from this point. We started investigation how we can achieve the ideal numbers. And we found that this is not the actual numbers you will get in your data centers. The problem is not a storage device. PBSS is very amazing technologies, but the problem is the conventional host-centric and CPU-centric architectures, they cannot fully utilize the high-end SSDs and petabyte SSDs. The bottom figure describes that real-world deployment scenario. To utilize the petabyte SSDs, you have to connect it to multiple clients through the high bandwidth network fabrics. And you have to run some storage infrastructure management software in a client and server side. So for example, you have to provide a NVMe device view for host applications, and you have to execute NVMe over fabric protocols to access the actual disaggregated NVMe devices at the remote node. And this protocol is running on some specific network protocol transport layers. For example, TCP/IP or RoCE v2 or InfiniBand. And this is the same story in the storage server side too. And this conventional design is very resource hungry, and it demands a lot of host CPU cores. This is why you cannot get the ideal performance numbers because of the bottleneck on the CPU side. These days, the people call it data center tax or storage tax in a data center, which means you have to pay very valuable resources like host CPU cores, or you have to pay a lot of actual money to get the high-end SSDs in your data centers. That's why we first focus on NVMe over TCP acceleration on DPU for this project. And our solutions are not relying on some small and embedded processor on FPGA board, or the major data paths and data processing are accelerated in our customized architectures on FPGA. And another thing is that we provide abstraction layer, and we hide all the complexity under a standard NVMe interface. So the users will see our DPU as a standard local NVMe devices, but inside the DPU, this will be translated into NVMe over fabric context, and the messages between clients and servers are encapsulated or decapsulated through our TCP/IP offloading engines. And our product is implemented on the FPGA chips, so we can provide some customization solutions as well. And we got many feedback from multiple sources, and they always say that it must be super easy to adopt in the real world. That's why we chose TCP/IP as an underlying network transport layer, because it has a very long history. So people are already familiar with it, and it is a standard. So it has a many well-defined ecosystem, like network switches from multiple different vendors. So with our solution, users do not have to learn new mechanisms to configure our DPU. And at the same time, users don't have to buy new network switches or network cables to use our solutions. So our final design goal is achieving high performance and high scalability, while at the same time while maintaining the standard and the flexibility in TCP/IP stacks. And this is our evaluation setup for the case study. We installed 2 U55C boards from Xilinx, and each one has 2 times 100 gig network ports. So the aggregate bandwidth is 400 gig and per direction. And for the client side, we installed 1 U55C card per server, so that it can saturate up to 200 gig. And we offloaded TCP IP and NVMe stacks on client side, and we offloaded only TCP IP stacks on the server side. And I'm going to talk about the server side first. First, we measure the read and write performance with the increasing number of SSDs. The interesting point is that the software NVMe TCP baseline cannot achieve scalable throughput, and its performance is limited around the 200 gigabit per second with fully utilizing 32 AMD CPU cores. But with our technologies, the PBSSD can achieve around the 400 gig, and we believe that with more PCI lanes and higher PCI generations and more DPU cards, we'll move the current point to the ideal point around 1.6 terabps. So the bottom line is, we eventually need DPU, and we eventually need some hardware acceleration solutions on DPU, because the current CPU cores are not efficient to handle the modern storage stacks beyond 100 gigabit per second. And this slide summarizes the performance and host CPU efficiency, and our DPU enhanced solution can provide the full duplex performance, so the 400 gig per direction, and the aggregate will be 800. And at the same time, our DPU can save a lot of CPU cores. By offloading TCP IP stacks to the hardware, we can save around 15 cores, and eventually we can save the rest of all the cores by integrating NVMe target offloading IP into our DPU solutions. And this is very preliminary study on TCO analysis. We made a custom model to expect the TCO reduction and found that our DPU can reduce TCO up to 20% with the current specification. There are two major sources for this benefit. One is our DPU enables higher performance per server. So the users can satisfy their performance score with a fewer number of servers. And the second thing is DPU enhanced PBSSD will have lower power usage per server due to the reduced CPU utilizations. Okay, we covered the storage side and what happened to the client side on the left. We also applied NVMe initiator offloading feature in those servers. So let's talk about the client side too. So again, this slide summarizes the performance and host the CPU efficiency in client side. The DPU enhanced the servers outperform software baseline in terms of full duplex throughput, and it reduced the core utilization more than 10 cores. But we still need some CPU cores for user applications. In this case, FIO is the user application, so depending on the user's target application, we can save more CPU cores and make them used for other data processing or turned off to reduce the TCO of the server. And this is a very interesting use case. One of our use cases in client side is that we can put more GPUs in a single computation server so that they can boost AI performance in a MLPerf benchmark. This MLPerf storage benchmark results with this remote storage configuration. The gray region shows the software baseline. Because it demands of a lot of CPU cores to feed data to GPU, a lot of accelerators and GPUs, the performance was saturated due to the CPU bottleneck at around 40 samples per second. But and some software optimization can be helpful. If you look at the circle in the middle, there was one of submission from Weka, and they get better results compared to the NVMe over TCP software baseline. And the yellow circle at the right shows our points. We freeze up CPU resources so that we can accommodate more GPUs in a server. And as a result, we outperform the software implementation. And the bottom line is the DPU, Mangoboost DPU can scale up the performance per server, and this will help improving cost effectiveness in large-scale infra for AI workload. And this is a summary. So So we introduced some collaboration work with Samsung and Mangoboost, and there are some future work. So we will integrate with other software features like RAID or data compression or some data protection features in our DPU solutions. Also, we are planned to integrate some system-level power management solution in our DPU. And we run our booths at the export hall. So please come and join our booth. I will be there, and our leadership and our engineering team will be there. Thank you.